Welcome to DREAMLAB Knowledge, where tonight we venture into the deepest shadows of human understanding, exploring the profound question that keeps scientists awake at night and philosophers pondering across centuries. We stand at a remarkable moment in the history of science, a time when we've mapped the human genome, photographed black holes, and sent machines to Mars. We've split the atom, discovered the fundamental particles that compose reality, and peered back to within moments of the universe's birth. Yet for all these triumphs, for all the mysteries we've solved, and the knowledge we've accumulated, there remain vast territories of ignorance, fundamental questions about reality itself that continue to elude our most brilliant minds and most sophisticated instruments. These are not minor puzzles waiting for slightly better technology or another decade of research. These are the mysteries that strike at the very foundation of existence. They challenge our assumptions about the nature of reality, the essence of consciousness, the arrow of time, and the origins of everything we see around us. Some of these questions have been asked for thousands of years. Others have emerged only recently as our instruments grew powerful enough to detect phenomena that raise more questions than they answer. All of them remind us that despite our technological prowess and accumulated wisdom, we remain humbled travelers in a universe far stranger and more mysterious than we ever imagined. Close your eyes for a moment and consider the strangeness of your own existence. You are conscious, aware of these words, aware of your own thoughts, perhaps aware of the room around you, or the sensations in your body. This consciousness, this subjective experience of being you, is so immediate and undeniable that it seems to be the most certain thing in your life. Yet if you asked a neuroscientist to explain how the 3 pounds of biological tissue inside your skull generates the vivid theater of consciousness, they would have to admit that despite decades of brain imaging studies and thousands of research papers, we still don't really know. We can point to correlations between brain activity and conscious experience. We can even predict some aspects of what you're thinking by watching which neurons fire in your brain. But explaining how and why electrochemical signals racing through neural circuits produce the subjective feeling of what it's like to be you, that remains one of the deepest mysteries in all of science. The hard problem of consciousness. Let's begin our journey with perhaps the most intimate mystery of all, the nature of consciousness itself. Philosophers call this the hard problem of consciousness, a term coined by philosopher David Chalmers to distinguish it from the easy problems of consciousness. Now, when philosophers call something easy, they're being somewhat ironic. The easy problems include figuring out how the brain processes information, how it integrates data from different senses, how it controls behavior, how attention works, and how we distinguish sleep from wakefulness. None of these questions are actually easy. They've occupied armies of neuroscientists for decades and will likely continue to do so for decades more. But they're easy in the sense that we can imagine how to solve them. We can design experiments, build better brain scanners, trace neural pathways, and gradually chip away at understanding the mechanisms involved. The hard problem is different. It asks, why is there any subjective experience at all? Why doesn't all this neural information processing happen in the dark, so to speak, without anyone being home to experience it? Why is there something it feels like to see the color red, to taste chocolate, to feel pain, to experience joy? Philosophers use a special term for these subjective qualities of experience. They call them qualia. The redness of red, the painfulness of pain, the particular character of what it's like to hear middle C played on a piano, these are qualia. To understand why this is so puzzling, consider a thought experiment that philosopher Frank Jackson proposed called Mary's Room. Imagine a brilliant neuroscientist named Mary who has spent her entire life in a black and white room. She's never seen colors. but through black and white books and lectures on a black and white television, she's learned everything there is to know about the physical properties of color. She knows all about wavelengths of light, how photons strike the retina, how signals travel down the optic nerve, which neurons fire in the visual cortex when someone sees red versus blue. She knows more about the science of color than any person has ever known. One day, Mary is released from her room and sees color for the first time. She sees a ripe red tomato. The question is, does she learn something new? Most people's intuition says yes. Clearly, she learns what it's actually like to see red, even though she already knew all the physical facts about red. But if that's true, it suggests there's something about consciousness, about subjective experience, that isn't captured by physical facts alone. This is deeply troubling for a scientific worldview that wants to explain everything in terms of physics, chemistry, and biology. It suggests there might be an explanatory gap between the objective, third-person facts about brains and the subjective, first-person facts about experience. Some neuroscientists dismiss the hard problem as a confusion or as unscientific navel-gazing. They argue that once we fully understand the neural mechanisms of perception, attention, and memory, consciousness will be explained and the mystery will dissolve. Daniel Dennett, one of the most prominent critics of the hard problem, argues that consciousness is not the mystery it appears to be, that the sense of a rich inner life is itself an illusion created by the brain's information processing. According to Dennett, when we fully explain the functional mechanisms of the brain, we will have explained consciousness itself, and the intuition that something more is needed will be revealed as a cognitive error. But others, including many thoughtful scientists and philosophers, recognize that the hard problem points to something genuinely puzzling that won't dissolve through better neuroscience alone. How does matter give rise to mind? How do objective physical processes create subjective experience? The philosopher Thomas Nagel explored this question in his famous essay, "What is it like to be a bat?" He argued that even if we knew everything about a bat's brain and behavior, we still wouldn't know what it's like to experience the world through echolocation, to perceive space through reflected sound waves. There's a subjective character to experience that seems to escape objective scientific description. Various theories have been proposed to bridge this explanatory gap. Some scientists suggest consciousness arises from specific patterns of neural activity, perhaps involving gamma wave oscillations in the brain or information integration across widely distributed brain networks. When you look at a red apple, neurons in your visual cortex fire in synchronized patterns, creating what neuroscientists call a neural assembly. Perhaps consciousness is just what these synchronized patterns feel like from the inside. But this raises the question, why should synchronized neural firing feel like anything at all? The integrated information theory, developed by neuroscientist Giulio Tononi, takes a more radical approach. This theory proposes that consciousness corresponds to integrated information that exists in a system as a whole and cannot be reduced to the sum of its parts. According to this view, any system that integrates information in the right way would be conscious to some degree. A simple thermostat integrates minimal information and might have an infinitesimal degree of consciousness. A human brain integrates vast amounts of information and has rich, complex consciousness. A digital computer running the same algorithms as a brain might have identical information integration and therefore identical consciousness. This theory makes the striking prediction that consciousness is a fundamental property measured by a quantity called phi, which captures how much information is integrated in a system. Systems with high phi are highly conscious. Systems with low phi are barely conscious or not conscious at all. The theory has inspired experiments attempting to measure consciousness in patients with disorders of consciousness, trying to distinguish vegetative states from minimally conscious states, by measuring information integration in their brains. Another influential framework is the global neuronal workspace theory, developed by cognitive neuroscientists Stanislas Dehaene and others. This theory suggests that consciousness arises when information becomes globally available across the brain's workspace, accessible to various cognitive systems. Think of the brain as containing many specialized processors working in parallel, some handling visual information, others processing language, still others managing motor control or memory retrieval. Most of this processing happens unconsciously, but when information enters a global workspace, broadcast to many different brain systems simultaneously, it becomes conscious. Consciousness, in this view, is global information availability. The global workspace theory can explain many features of consciousness. It accounts for the limited capacity of consciousness. We can only hold a few things in conscious awareness at once because the global workspace has limited bandwidth. It explains the relationship between consciousness and reportability. We can report what we're conscious of because that information is globally available to the language systems. It predicts that damage to the global workspace network should impair consciousness, which aligns with observations from brain injury patients. But none of these theories truly solve the hard problem. They tell us about the neural correlates of consciousness, the brain activities associated with conscious experience. But correlation isn't explanation. Knowing that certain patterns of brain activity accompany consciousness doesn't tell us why those patterns feel like anything at all. Why does global information availability feel like seeing red rather than simply being an unconscious information broadcast? Why does integrated information have an inner feeling at all, rather than just being integrated information in the dark? The gap between objective description and subjective experience remains. Consider another thought experiment, this one proposed by philosopher Ned Block. Imagine we could replace individual neurons in your brain, one at a time, with tiny silicon chips that perfectly replicate each neuron's input-output behavior. After each replacement, you still behave exactly the same way, since the artificial neuron functions identically to the biological one it replaced. Eventually, your entire brain has been replaced with silicon chips, but you still act and talk exactly as before. Would you still be conscious? If so, at what point during the gradual replacement process did consciousness disappear? Or does consciousness fade gradually? This thought experiment reveals our uncertainty about what physical properties are necessary for consciousness. The hard problem becomes even more perplexing when we consider that consciousness seems to have causal effects in the world. You feel pain, and that feeling causes you to pull your hand away from the hot stove. You see a beautiful sunset, and that experience causes you to pause and appreciate it. But if consciousness is somehow separate from or irreducible to physical brain processes, how can it cause physical effects? And if consciousness is just physical brain processes, we're back to the original puzzle of why these processes should feel like anything. Some philosophers and scientists have proposed more radical solutions. Perhaps they suggest consciousness is a fundamental feature of the universe, like mass or charge, not reducible to anything simpler. This view, called panpsychism, has a long philosophical history stretching back to ancient times, but it has recently gained renewed attention from some contemporary philosophers and even a few physicists. The idea is that some form of experience might be present even in simple physical systems, with human consciousness being an enormously complex version of something that exists in protoform throughout nature. According to panpsychism, an electron might have an infinitesimally simple form of experience, not thoughts or emotions, but perhaps something like a primitive feeling of charge or spin. A molecule would have a slightly more complex form of experience arising from the combination of its constituent atoms. A brain with its billions of neurons arranged in intricate networks would have vastly richer experience. This view avoids the problem of explaining how consciousness emerges from non-conscious matter because it proposes that all matter has some degree of consciousness. The question becomes not how does matter create consciousness, but how does simple consciousness combine into complex consciousness? Panpsychism faces its own challenges, of course. The combination problem asks, how do billions of tiny micro-experiences in individual neurons combine into the unified experience of being you? Why don't we experience ourselves as billions of separate consciousnesses rather than one integrated whole? And how could we ever test whether an electron or an atom has experience? If panpsychism makes no testable predictions, is it really science or just speculative metaphysics? Other thinkers propose that we need entirely new physics to understand consciousness. Some researchers have explored whether quantum effects in the brain might play a role. The physicist Roger Penrose and anesthesiologist Stuart Hameroff proposed that consciousness arises from quantum computations in cellular structures called microtubules inside neurons. According to their theory, the brain operates as a quantum computer, and consciousness emerges when quantum wave functions collapse in a specific way governed by quantum gravity effects. This orchestrated objective reduction theory, as they call it, would link consciousness to fundamental physics in a way that current neuroscience doesn't consider. Most neuroscientists are skeptical of quantum consciousness theories. The brain is a warm, wet, noisy environment, exactly the kind of place where quantum effects should rapidly decohere and disappear. Maintaining the delicate quantum states necessary for quantum computation would seem impossible in brain tissue. But Penrose and Hameroff argue that microtubules might be able to shield quantum effects from environmental decoherence. So far, experimental evidence for quantum effects in the brain remains controversial and inconclusive. The mystery of consciousness becomes even more pressing when we consider artificial intelligence. As we build increasingly sophisticated AI systems capable of perceiving, learning, reasoning, and even conversing in seemingly thoughtful ways, questions about machine consciousness become urgent. Large language models can write essays, answer questions, and engage in discussions that seem intelligent. But are they conscious? Is there something it's like to be ChatGPT? Or are these systems just sophisticated information processors with no inner experience, no matter how convincingly they mimic conscious behavior? The question isn't merely academic. If we create conscious AI, we would have moral obligations toward these systems. Conscious beings can suffer, can have interests, can deserve moral consideration. But if we're unsure whether human consciousness is just complex information processing or something more, how can we determine whether machines that process information are conscious? Some philosophers argue we could never know. A sufficiently sophisticated AI could perfectly mimic all the outward signs of consciousness without having any inner experience. This is essentially the philosophical zombie thought experiment applied to machines. Others suggest that certain functional properties might be sufficient for consciousness. If a system can model itself, can distinguish itself from its environment, can process information in an integrated way, can learn from experience and modify its behavior accordingly, perhaps these functional capacities are what consciousness is, regardless of whether the system is made of biological neurons or silicon chips. From this functionalist perspective, consciousness is multiply realizable. Different physical substrates could support the same conscious experiences as long as they implement the same functional relationships. The uncertainty about machine consciousness connects to deeper questions about the relationship between consciousness and intelligence. Could a system be highly intelligent without being conscious? Could a system be conscious without being intelligent? We tend to assume consciousness and intelligence go together, but they might be separable properties. A patient in a vegetative state might retain some forms of consciousness, perhaps experiencing sensations or emotions, without the cognitive capabilities we associate with intelligence. Conversely, an AI system might exhibit brilliant problem-solving and pattern recognition without any experiential inner life whatsoever. The origin of life. Let's shift our attention from the mystery of consciousness to another fundamental question that continues to perplex scientists. How did life begin? This question has captivated humanity for millennia, but even with all our modern scientific knowledge, the origin of life remains shrouded in uncertainty. We know when life appeared on Earth. The earliest fossil evidence places simple microorganisms on our planet roughly 3.8 billion years ago, only a few 100 million years after the Earth's surface had cooled enough to permit liquid water. But knowing when doesn't tell us how. The challenge of understanding life's origin, what scientists call abiogenesis, is immense. Life as we know it is extraordinarily complex, even in its simplest forms. A single bacterial cell contains hundreds of genes encoded in DNA, sophisticated protein machinery for reading and copying that DNA, elaborate metabolic pathways for extracting energy from nutrients, membranes that maintain the cell's internal environment, and intricate systems for sensing and responding to the world. All of these components work together in an integrated system of staggering complexity. The question is, how could such a system arise from non-living chemistry? Charles Darwin himself recognized the difficulty of this question. In an 1871 letter, he speculated about a warm little pond where organic compounds might accumulate and eventually give rise to life. But he also wrote to a colleague, "It is mere rubbish thinking at present of the origin of life. One might as well think of the origin of matter." Despite Darwin's pessimism, scientists throughout the 20th century made significant progress in understanding how life's building blocks might have formed on early Earth. The famous Miller-Urey experiment of 1952 showed that amino acids, the building blocks of proteins, could form spontaneously when scientists simulated conditions thought to exist on early Earth. Harold Urey and his graduate student Stanley Miller sealed water, methane, ammonia, and hydrogen in a flask, then sent electrical sparks through the mixture to simulate lightning. Within days, they detected amino acids in the solution. This was a revolutionary finding, suggesting that life's chemical components might arise naturally from simple chemical reactions. The experiment captured public imagination and seemed to bring the origin of life problem within reach of scientific solution. But we now know that the early Earth's atmosphere probably had a different composition than Miller and Urey assumed. More recent models suggest the atmosphere contained more carbon dioxide and nitrogen, less methane and ammonia. When scientists repeat the Miller-Urey experiment with these updated atmospheric compositions, they still get organic molecules, but the yields are lower and the reaction products are different. This doesn't invalidate the fundamental insight that organic molecules can form through natural processes, but it complicates the picture of exactly how it happened on early Earth. Moreover, amino acids, while necessary for life, are just one piece of an enormously complex puzzle. Building amino acids is one thing, assembling them into functional proteins is quite another. Modern proteins typically contain hundreds of amino acids arranged in precise sequences, folded into elaborate three-dimensional structures essential for their function. A single mutation, changing just one amino acid in the sequence, can sometimes completely destroy a protein's function. How could random chemical processes produce even one functional protein, let alone the dozens of different proteins a minimal cell requires? The odds seem astronomically small. There are 20 different amino acids used in proteins. A small protein might contain 100 amino acids. The number of possible sequences is 20 to the power of 100, a number so large it dwarfs the number of atoms in the observable universe. The vast majority of these sequences wouldn't fold into stable structures or perform useful functions. Finding functional proteins in this vast space of possibilities seems impossibly improbable if you're just trying random combinations. But life didn't start with modern proteins. The first proteins were probably much simpler, perhaps just short chains of a few amino acids with crude catalytic activity, and they didn't need to be perfect. They just needed to be better than nothing, conferring some advantage that would lead to their preferential replication. Evolution doesn't require optimal solutions, just incremental improvements. Still, explaining how even simple functional proteins arose remains challenging. And proteins are just one class of biomolecules. Life also requires nucleic acids like DNA and RNA for storing genetic information, lipids for creating cell membranes, and carbohydrates for energy storage. Modern cells use all these different types of molecules in an integrated system. DNA stores genetic information in a stable, long-term format. RNA transcribes that information and helps translate it into proteins. Proteins do the work of the cell, catalyzing reactions, transporting molecules, responding to signals. Lipids form membranes that enclose the cell and create internal compartments. Carbohydrates provide energy and structural support. How did all these different types of molecules come together to create the first living cell? One influential hypothesis, called the RNA world hypothesis, proposes that early life was based on RNA rather than DNA and proteins. This idea emerged from the discovery that RNA molecules can do something remarkable. They can both store genetic information, like DNA, and catalyze chemical reactions, like proteins. This dual functionality makes RNA a plausible candidate for a simpler precursor to modern life, where a single type of molecule could handle both information storage and metabolism. In the 1980s, scientists discovered RNA molecules called ribozymes that can catalyze their own replication and even splice themselves. Thomas Keck and Sidney Altman won the Nobel Prize for discovering that RNA molecules could act as enzymes, shattering the dogma that all biological catalysts must be proteins. This discovery made the RNA world hypothesis much more plausible. If RNA could replicate itself and catalyze reactions, perhaps early life consisted of self-replicating RNA molecules, with DNA and proteins evolving later as more sophisticated molecules that took over specialized functions. DNA for more stable information storage, proteins for more diverse and efficient catalysis. Scientists have demonstrated in the laboratory that RNA molecules can evolve new functions through a process called in vitro evolution, or CELEX. Starting with a random pool of RNA sequences, researchers can select for molecules that bind to specific targets or catalyze particular reactions, then amplify and mutate the successful sequences, repeating the process for multiple generations. Through this directed evolution, scientists have created RNA enzymes that perform reactions never seen in nature, suggesting that RNA has enormous potential for functional diversity. The RNA world hypothesis elegantly solves some puzzles, but creates others. If RNA came first, where did the first RNA molecules come from? RNA nucleotides, the building blocks of RNA, are themselves complex molecules containing three components: a sugar, ribose, a nitrogen-containing base, and a phosphate group. These components are difficult to synthesize under plausible prebiotic conditions and even more difficult to assemble into complete nucleotides. The ribose molecule is particularly problematic. It's unstable and difficult to produce selectively, among other similar sugars that would also form under prebiotic conditions. In 2009, chemist John Sutherland and colleagues made a breakthrough by showing that RNA nucleotides might be synthesized through a different pathway than biologists had assumed. Rather than building the sugar, base, and phosphate separately and then combining them, Sutherland found that simpler starting molecules, compounds like cyanamide and glycolaldehyde that would plausibly exist on early Earth, could react to form activated nucleotides directly through a series of chemical steps. The reactions required specific conditions, the right pH, the right minerals to catalyze certain steps, ultraviolet light, but these conditions seemed geologically plausible. More recently, Sutherland extended this work to show that similar starting materials and conditions could produce not just nucleotides, but also amino acids and lipid precursors. This suggests the tantalizing possibility that all of life's major building blocks might have arisen through related chemical pathways in the same environment, rather than requiring separate explanations for how each class of biomolecule formed. If true, this would make the origin of life seem more chemically inevitable and less absurdly improbable. Another approach to the origin of life question focuses on metabolism rather than genetics. These metabolism-first hypotheses suggest that before there was genetic information or self-replication, there were networks of chemical reactions that could capture energy and synthesize organic molecules. Perhaps life began not with a self-replicating molecule, but with a self-sustaining metabolic network. Think of it like this. Modern life uses genetic information to build the metabolic machinery, but perhaps in early life, the metabolic machinery came first and genetic information evolved later as a way to make metabolism more reliable and efficient. Proponents of metabolism-first theories point to certain chemical reaction cycles that occur spontaneously under the right conditions and bear resemblance to metabolic cycles in modern cells. The reverse citric acid cycle, for instance, is a key metabolic pathway in some modern bacteria that can fix carbon dioxide into organic molecules. Under the right conditions, this cycle, or something like it, might run spontaneously, driven by energy gradients without requiring enzymes. The cycle would produce organic molecules that could accumulate and participate in further reactions, gradually building up chemical complexity. Some researchers point to hydrothermal vents on the ocean floor as possible sites for this early metabolism. Hydrothermal vents are openings in the Earth's crust where superheated mineral-rich water gushes upward from beneath the seafloor, mixing with cold seawater. These environments have several appealing features for the origin of life. They provide abundant chemical energy in the form of reduced minerals and chemical gradients. They create natural compartments in their porous mineral structures that could concentrate organic molecules. They stay stable for thousands or even millions of years, providing the long timescales necessary for chemical evolution to occur. And they exist independently of sunlight, which would have been dangerous on early Earth before the ozone layer formed to shield the surface from UV radiation. One particular type of hydrothermal vent, called alkaline hydrothermal vents or white smokers, has attracted special attention. These vents produce warm, around 60 to 90 degrees Celsius, alkaline hydrogen-rich fluids. Where this fluid meets the acidic seawater, minerals precipitate and form chimney structures riddled with tiny pores. Remarkably, these structures create natural pH gradients and electrochemical gradients similar to those that modern cells use to generate energy through chemiosmosis, the process by which cells make ATP, the energy currency of life. In modern cells, this energy generation occurs across cell membranes. An ion gradient, typically of protons, is maintained across a membrane, with more protons on one side than the other. The proton's natural tendency to flow down this gradient, from high concentration to low, drives molecular turbines called ATP synthase that generate ATP. It's like a water wheel, powered by flowing ions. In hydrothermal vent structures, similar gradients arise naturally across the mineral barriers, separating alkaline vent fluid from acidic seawater. The proposal is that early metabolic reactions might have harnessed these naturally occurring gradients before cells evolved their own membranes and the ability to maintain gradients independently. The geochemist Michael Russell has championed this hydrothermal vent scenario for the origin of life, arguing that the chemistry of these environments naturally drives the formation of organic molecules and provides the energy and conditions necessary for increasingly complex chemistry. The biochemist Nick Lane has extended these ideas, proposing that the fundamental energy metabolism of all life, the way cells extract energy from chemical reactions, reflects these ancient origins at alkaline hydrothermal vents. If the deep marine hydrothermal setting was indeed the site where life originated, then a biogenesis could have happened very early in Earth's history, potentially as early as 4.0 to 4.2 billion years ago, soon after the oceans formed. If life evolved at depths of more than 10 meters below the surface, it would have been shielded both from devastating asteroid impacts that regularly struck early Earth and from the intense ultraviolet radiation from the sun, which would have been lethal at the surface before oxygen accumulated in the atmosphere and formed a protective ozone layer. However, arguments against a hydrothermal origin of life exist as well. Some researchers note that the hyperthermophilic bacteria and archaea that thrive at the high temperatures of modern hydrothermal vents might represent not ancient life forms, but organisms that evolved to colonize these extreme environments later. The heat tolerance might be a derived characteristic rather than an ancestral one. Other scientists point out that while hydrothermal vents can produce some organic molecules, the concentrations are much lower than in laboratory simulations like the Miller-Urey experiment, sometimes lower by several orders of magnitude. Whether the low concentrations at vents could support the accumulation of organic molecules necessary for life remains debated. A third line of research examines how cell membranes might have formed. For life to exist as we know it, there must be some boundary separating the living system from its environment, creating an inside and an outside. Without compartmentalization, useful molecules would diffuse away, and harmful molecules from the environment would interfere with delicate chemical reactions. Modern cell membranes are sophisticated structures made of phospholipids, molecules with a water-loving head and a water-fearing tail. When phospholipids are placed in water, they spontaneously form bilayer membranes, with the water-fearing tails hidden inside and the water-loving heads facing the water on both surfaces. Simpler lipid molecules can also form membranes and even spontaneous vesicles, tiny spheres with a lipid membrane enclosing a water-filled interior. Scientists have demonstrated that these simple vesicles can grow by incorporating additional lipid molecules, can divide when mechanically stressed, and can selectively concentrate certain molecules in their interior. Some researchers believe that such protocells, simple vesicles that contain self-replicating molecules and rudimentary metabolism, might represent an intermediate step between non-living chemistry and fully living cells. Despite all this research spanning decades and involving scientists from chemistry, biology, geology, and physics, we still don't have a complete picture of how life originated. We have promising ideas about how various pieces of the puzzle might have fallen into place, how organic molecules formed, how RNA might have preceded DNA and proteins, how metabolic cycles could have arisen, how membranes assembled. But we haven't yet put all these pieces together into a coherent narrative that takes us step by step from simple chemistry to the first living cell. The transition from non-living chemistry to living biology remains murky, shrouded in deep time. Part of the difficulty is that we're trying to reconstruct events that happened nearly 4 billion years ago, leaving little direct evidence. The Earth's surface has been recycled many times through plate tectonics. The oldest rocks containing possible fossils have been altered by heat and pressure. We can never go back in time to observe what actually happened, never perform experiments under the exact conditions of early Earth. We're left with chemical logic, plausibility arguments, and laboratory demonstrations that certain steps could have happened without being able to prove that they did happen in the sequence and manner we imagine. The earliest life forms would have been much simpler than modern cells, lacking many of the sophisticated features that modern organisms possess. But even they would have been extraordinarily complex by the standards of non-living chemistry. The simplest free-living bacterium today has hundreds of genes and intricate molecular machinery. Even if we imagine the first life forms were 10 times simpler, they would still represent an enormous leap in complexity from a mixture of organic molecules. How do you bridge that gap? How do you get from a prebiotic soup of amino acids, nucleotides, and lipids to a self-replicating, evolving, metabolizing cell? One key insight is that early life didn't need to be efficient or optimized. Modern cells are the result of billions of years of evolution, honed by natural selection into highly efficient machines. The first cells could have been crude, sloppy, barely functional entities, as long as they could reproduce themselves with occasional errors, providing variation for natural selection to act upon. Evolution could gradually improve them. Scientists sometimes forget this when they evaluate whether a proposed early life form is plausible. They apply standards of efficiency and sophistication appropriate for modern organisms rather than recognizing that early life just needed to work well enough to outcompete non-living chemistry. Another crucial point is that the origin of life probably wasn't a single event, but a gradual process occurring over millions of years and possibly in multiple locations. There wasn't a moment when life suddenly sprang into existence. Rather, there was a long period of chemical evolution, during which increasingly complex and sophisticated chemical systems emerged, eventually crossing some threshold beyond which we would recognize them as alive. Exactly where that threshold lies is itself somewhat arbitrary. We define life using criteria like metabolism, reproduction, evolution, but these features might have emerged separately and gradually rather than all at once. Some scientists wonder whether life's origin was an extraordinarily improbable accident. Perhaps Earth got incredibly lucky, and life is exceedingly rare in the universe. If the origin of life required an unlikely series of fortunate circumstances, then most planets, even those with liquid water and the right chemistry, might remain eternally lifeless. From this perspective, we might be alone or nearly alone in a vast cosmos, where the conditions for life's emergence are extraordinarily rare and the actual emergence even rarer. Others argue that the emergence of life might be more inevitable than we think, that chemistry naturally tends toward increasing complexity under the right conditions, and that life should arise wherever those conditions exist. This view suggests that life is a natural consequence of chemistry and thermodynamics, that organized systems capable of capturing energy and replicating themselves will spontaneously emerge from sufficiently complex chemistry. The laws of physics and chemistry don't just permit life, they encourage it, favor it, make it almost inevitable given enough time and suitable conditions. From this perspective, the universe might teem with life, arising independently on countless worlds wherever conditions allow. We won't fully settle this debate until we either create life in the laboratory from scratch or discover life elsewhere in the universe. Creating synthetic life would demonstrate that the pathway from chemistry to biology is accessible through known processes, that we understand the principles well enough to engineer a living system de novo. Such an achievement would be one of the greatest triumphs in the history of science, comparable to splitting the atom or landing on the moon. Several research groups are working toward this goal, attempting to construct minimal cells from chemical components or to design artificial biochemistry that could support life in different ways than Earth's organisms. The discovery of life elsewhere would be equally revolutionary. If we found life on Mars or Europa or Enceladus, especially if that life used different biochemistry than Earth life, different amino acids, different genetic codes, different molecular machinery, it would strongly suggest that life arises readily wherever conditions permit. If we found life on Mars that shared a common ancestor with Earth life, suggesting that life originated on one planet and was transferred to the other via meteorites, it would tell us that life can survive and spread between worlds. If we found no life anywhere else, despite searching many promising locations, it might suggest that life's origin is indeed extraordinarily rare, perhaps requiring circumstances that occurred on Earth but rarely elsewhere. These questions extend beyond academic curiosity into humanity's self-understanding. Are we the universe's only way of knowing itself? A precious and possibly unique emergence of consciousness in an otherwise unconscious cosmos? Or are we one example among countless others, part of a living universe where consciousness arises repeatedly wherever matter and energy are arranged in sufficiently complex ways? The answer to how life began shapes our answer to the question of whether we're alone. The enigma of dark matter and dark energy. From the mystery of life's emergence, let's zoom out to the largest scales imaginable and confront one of the most humbling discoveries in the history of astronomy. The vast majority of the universe is made of stuff we cannot see and do not understand. When astronomers add up all the ordinary matter they can observe, all the stars and galaxies, all the gas and dust floating between them, all the planets and asteroids and comets, they find that it accounts for only about 5% of the total mass and energy content of the universe. 5%. The other 95% consists of two mysterious components that scientists have labeled with characteristic lack of imagination: dark matter and dark energy. The story of dark matter begins in the 1930s, when Swiss astronomer Fritz Zwicky studied a cluster of galaxies called the Coma Cluster. By measuring how fast galaxies in the cluster were moving, Zwicky could calculate how much mass the cluster must contain to keep those galaxies gravitationally bound together. His calculations revealed a problem. The galaxies were moving so fast that the cluster's visible matter couldn't possibly provide enough gravity to hold them together. The cluster should have flown apart long ago. Zwicky proposed that some invisible form of matter must be present, providing additional gravity. He called it Dunkel Materia, dark matter. For decades, Zwicky's idea remained on the fringes of astronomy. But in the 1970s, American astronomer Vera Rubin made observations that forced the scientific community to take dark matter seriously. Rubin studied how fast stars orbit in spiral galaxies. According to the laws of physics, stars farther from a galaxy's center should orbit more slowly, just as planets farther from the sun orbit more slowly. But Rubin found that stars at the edges of galaxies orbit just as fast as stars closer to the center. This flat rotation curve implied that galaxies must contain far more mass than we can see, distributed in a vast invisible halo extending well beyond the visible disk. Dark matter had to be real. Today, multiple independent lines of evidence confirm dark matter's existence, creating one of the most robust conclusions in modern cosmology, despite our ignorance about dark matter's nature. Astronomers have observed how light from distant galaxies gets bent as it passes through massive galaxy clusters. the gravitational lensing effect predicted by Einstein's general relativity. When light from a background galaxy passes near a massive cluster, the cluster's gravity bends the light's path, distorting the background galaxy's image into arcs or even complete rings. By measuring the amount of distortion, astronomers can map how much mass the cluster contains and where that mass is distributed. These gravitational lensing measurements consistently show that galaxy clusters contain far more mass than their visible matter can account for. The famous bullet cluster provides particularly compelling evidence. This system formed when two galaxy clusters collided at tremendous speed. In the collision, the hot gas that permeates each cluster, which contains most of the ordinary matter and glows brightly in X-rays, slammed together and stayed near the collision site, slowed by electromagnetic interactions. But the galaxies themselves and their dark matter halos pass through each other relatively unimpeded, since dark matter only interacts gravitationally and galaxies are mostly empty space. Gravitational lensing reveals that most of the mass in the system is not where the X-ray emitting gas is, but where the galaxies went, providing strong evidence for dark matter as a distinct substance rather than a modification of gravity. Scientists studying the cosmic microwave background radiation, the afterglow of the Big Bang that we detect as faint microwave radiation coming from all directions, find that its pattern of temperature variations can only be explained if about 27% of the universe's mass energy content is dark matter. The cosmic microwave background shows tiny temperature fluctuations, hotter spots and cooler spots at the level of 1 part in 100,000. These fluctuations reflect density variations in the early universe that would eventually grow into galaxies and galaxy clusters. The exact pattern of these fluctuations depends sensitively on the universe's composition. By measuring the pattern with exquisite precision using satellites like WMAP and Planck, cosmologists can determine how much ordinary matter, dark matter, and dark energy the universe contains. The data demand that dark matter exists and makes up about 5 times as much as ordinary matter. But here's the profound mystery. We have no idea what dark matter actually is. It doesn't absorb or emit light or any other electromagnetic radiation, which is why it's invisible to telescopes. It doesn't interact with ordinary matter through the electromagnetic force or the strong nuclear force that binds atomic nuclei together. It only interacts through gravity and possibly through the weak nuclear force, which would be why physicists sometimes call candidate dark matter particles WIMPs, weakly interacting massive particles. Dark matter isn't made of atoms, protons, neutrons, or electrons. It's not composed of any particle in the standard model of particle physics, the incredibly successful theory that describes all known particles and 3 of the 4 fundamental forces. Scientists have proposed various candidates for what dark matter might be. One leading possibility is that dark matter consists of new particles beyond the standard model. WIMPs are a favored candidate. Particles with masses perhaps 10 to 1,000 times a proton's mass that interact only weakly with ordinary matter. If WIMPs exist, they would have been produced in abundance in the hot early universe, and the right density of them would naturally remain today to account for the dark matter we observe. Supersymmetry, a proposed extension of the standard model, predicts the existence of several particles that could serve as WIMPs, though experiments at particle colliders, like the Large Hadron Collider, haven't yet found evidence for supersymmetry. Physicists have built elaborate detectors deep underground, shielded from cosmic rays, trying to catch the rare interaction of a dark matter particle passing through ordinary matter. These experiments use tanks of ultra-pure xenon or other materials, cooled to extremely low temperatures, waiting for the tiny flash of light or heat that would signal a dark matter particle colliding with an atomic nucleus. Despite decades of searching with increasingly sensitive detectors, no convincing dark matter signal has been detected. The absence of detections has ruled out many of the parameter space where WIMPs might exist, leading some physicists to wonder whether dark matter is something else entirely. Another candidate is the axion, a hypothetical particle much lighter than a WIMP, proposed to solve a different problem in particle physics, but which could also serve as dark matter. Axions would interact even more weakly with ordinary matter than WIMPs, making them extraordinarily difficult to detect. But several experiments are now searching for them, using sophisticated techniques that could catch actions converting into photons in strong magnetic fields. A more exotic possibility is that dark matter consists of primordial black holes. Black holes formed in the early universe, not from stellar collapse, but from density fluctuations in the Big Bang itself. These primordial black holes could have a wide range of masses, from microscopic to thousands of solar masses. If they exist in the right numbers, they could account for dark matter without requiring any new particles. However, various observations constrain how abundant primordial black holes of different masses can be, and it's unclear whether enough could exist to explain all dark matter. The possibility that dark matter might not be a particle at all, but rather a modification to the laws of gravity, has also been explored. Modified Newtonian dynamics, or MOND, proposes that gravity behaves differently than Newton and Einstein described when accelerations are extremely small, as they are on the outskirts of galaxies. MOND can successfully explain the flat rotation curves of spiral galaxies without invoking dark matter. However, MOND struggles to explain other observations like gravitational lensing and the cosmic microwave background, and most physicists favor dark matter over MOND. Nevertheless, the MOND idea reminds us that we should remain open to revolutionary possibilities, rather than assuming dark matter must be a new particle just because that's the conventional expectation. If dark matter is mysterious and humbling, dark energy is even more baffling and philosophically disturbing. Its discovery came as a complete shock to astronomers, overturning centuries of assumptions about the universe's evolution. For most of the 20th century, scientists assumed that the universe's expansion, set in motion by the Big Bang, must be gradually slowing down due to gravity's attractive force pulling galaxies toward each other. The question was merely how fast this deceleration was occurring. If the universe contained enough matter, gravity would eventually halt the expansion and reverse it, leading to a big crunch where everything collapses back together. If the universe contained less matter, it would expand forever, but the expansion would gradually slow, asymptotically approaching some final rate. In the 1990s, two independent teams of astronomers set out to measure exactly how fast this deceleration was occurring. They studied Type Ia supernovae, exploding white dwarf stars that serve as excellent standard candles for measuring cosmic distances because they all have similar intrinsic brightness. By measuring how bright these supernovae appear from Earth and comparing to how bright they actually are, astronomers can determine how far away they are. By measuring the redshift of their light, how much the light has been stretched to longer wavelengths by the expansion of space, astronomers can determine how fast the universe was expanding when that light was emitted. Combining many such measurements, astronomers could trace how the expansion rate has changed over billions of years of cosmic history. Both teams expected to measure a deceleration. Both teams found instead that the universe's expansion isn't slowing down at all. It's speeding up. Galaxies are accelerating away from each other. The expansion rate has been increasing for roughly the past 5 billion years. This was so unexpected, so contrary to theoretical expectations, that both teams initially thought they must have made an error. They checked and rechecked their data, looked for systematic errors, tried to find alternative explanations, but the signal remained. The universe's expansion is accelerating. This acceleration implies the existence of something with a repulsive gravitational effect, pushing galaxies apart with a force that overcomes gravity's attraction. This mysterious energy, dubbed dark energy by cosmologist Michael Turner, constitutes roughly 68% of the universe's total mass energy content, even more than dark matter. Unlike dark matter, which clumps together in halos around galaxies, dark energy appears to be uniformly distributed throughout space, the same density everywhere. Its repulsive effect becomes more dominant over large distances and at later times in cosmic history, which is why the universe's expansion only began accelerating a few billion years ago rather than right from the beginning. The discovery of dark energy earned the leaders of the two teams, Saul Perlmutter, Brian Schmidt, and Adam Rees, the 2011 Nobel Prize in Physics. But the prize recognized the discovery, not an explanation. The nature of dark energy remains one of the deepest mysteries in all of physics, perhaps the most profound problem at the intersection of cosmology, quantum mechanics, and gravity. Some physicists think dark energy might be related to the cosmological constant, a term that Einstein introduced into his equations of general relativity. Einstein originally added this constant to make his equations predict a static universe, neither expanding nor contracting, because he believed the universe must be eternal and unchanging. When Edwin Hubble discovered in 1929 that the universe is actually expanding, Einstein abandoned the cosmological constant, reportedly calling it his biggest blunder. But a cosmological constant would produce exactly the repulsive gravitational effect needed to explain the accelerating expansion. Interpreted in quantum field theory, the cosmological constant would represent the energy density of empty space itself, the vacuum. Quantum field theory predicts that even empty space should contain energy from virtual particles that constantly pop in and out of existence, borrowing energy from the vacuum for fleeting moments allowed by Heisenberg's uncertainty principle. These quantum fluctuations should contribute to the vacuum energy density. The problem is that when physicists calculate what this vacuum energy density should be using standard quantum field theory, they get an answer that's vastly, absurdly larger than what we observe, off by a factor of 10 to the 120th power, a number so large it's difficult to comprehend. This is one of the worst predictions in the entire history of science. Something is catastrophically wrong with either our understanding of quantum mechanics, our understanding of gravity, or our understanding of how they connect. Some physicists propose that dark energy might not be constant, but instead a new fundamental field permeating the universe, something they call quintessence, named after the ancient Greek concept of a fifth element beyond earth, air, fire, and water. Unlike the cosmological constant, which remains constant in space and time, quintessence could vary, potentially even changing its strength over cosmic history or from place to place. Different models of quintessence predict different behaviors for how dark energy has evolved and will evolve, potentially offering ways to distinguish between quintessence and a true cosmological constant through precision measurements of the universe's expansion history. Other physicists wonder whether dark energy signals that our theory of gravity itself needs modification. Perhaps Einstein's general relativity, while extraordinarily successful at describing gravity from the scale of the solar system up to galaxy clusters, breaks down on the largest scales, the scale of the observable universe. Maybe the accelerating expansion doesn't require dark energy at all, but rather reflects new gravitational physics that we've yet to discover. Proposed modifications to general relativity, with names like FR gravity or massive gravity theories, attempt to explain the acceleration without introducing dark energy. However, these theories face their own difficulties and generally struggle to match the full range of cosmological observations as well as dark energy does. The implications of dark energy are profound and deeply unsettling. If dark energy is real and its repulsive force continues to dominate the universe's evolution, the cosmos faces a cold and lonely future. The universe will expand faster and faster forever. Eventually, distant galaxies will recede from us at speeds faster than light. Not because they're moving through space faster than light, which relativity forbids, but because space itself is expanding, carrying them away. These galaxies will disappear from our observable universe, their light so redshifted that it becomes undetectable. In the far future, our local group of galaxies will become isolated, surrounded by an ever-growing bubble of space devoid of other galaxies. Stars will eventually exhaust their fuel and die. New stars will stop forming once all available gas is consumed. The universe will grow dark and cold. If dark energy's strength increases over time, an even more dramatic fate awaits. In a scenario cosmologists call the Big Rip, the expansion could accelerate so rapidly that it eventually tears galaxies apart, then solar systems, then planets, then atoms, then atomic nuclei themselves, ripping the fabric of space so violently that literally everything gets shredded. This would occur perhaps 20 billion years from now if dark energy behaves in this way. Alternatively, if dark energy somehow weakens or reverses, gravity might eventually overcome the expansion, leading to a big crunch where the universe collapses back to a singularity, possibly to bounce and expand again in a cyclic model. But current observations give no hint that dark energy is weakening. If anything, the expansion seems to be accelerating steadily or even potentially speeding up further. What bothers many physicists most is that we're in the dark about 95% of the cosmos. Imagine if a biologist said, "I understand 5% of living organisms, and the other 95% is completely unknown to me." That's essentially where astronomy stands today regarding the universe's composition. Dark matter and dark energy aren't minor gaps in our knowledge. They're gaping chasms, fundamental blind spots that suggest our current understanding of physics is radically incomplete. The puzzle of biological aging. Let's return from cosmic scales to a mystery that's intensely personal. Why do we age? From the moment we're born, we're on a journey toward inevitable decline. Our cells accumulate damage, our tissues lose their resilience, our organs gradually fail. This process is so familiar, so seemingly inevitable, that we rarely stop to ask, but why? Why does the sophisticated machinery of life, capable of growing from a single cell into a complex organism, eventually prove incapable of maintaining that organism indefinitely? Some species seem almost immortal. Certain jellyfish can revert to earlier life stages and start over. Hydra don't seem to age at all, and Greenland sharks can live for 400 years. So why can't we? The question of why we age is actually two questions tangled together. First, there's the evolutionary question. Why has natural selection produced organisms that age rather than organisms that maintain themselves indefinitely? Second, there's the mechanistic question. What biological processes actually cause aging at the cellular and molecular level? Both questions remain hotly debated among scientists. The evolutionary puzzle is particularly perplexing because aging seems maladaptive. If an organism could maintain itself in prime condition indefinitely, it could continue reproducing indefinitely, spreading its genes far more widely than an organism that ages and dies. So why don't we see selection favoring perpetual youth and immortality? The answer most evolutionary biologists give involves a concept called the disposable soma theory. This theory proposes that organisms face a fundamental trade-off between reproduction and maintenance. Energy and resources are limited. so an organism must allocate them strategically. Investing heavily in reproduction means less investment in maintaining and repairing the body. Investing heavily in maintenance might mean fewer offspring. From an evolutionary perspective, what matters is not how long you live, but how many offspring you produce who survive to reproduce themselves. For most organisms throughout evolutionary history, external hazards like predation, disease, and starvation meant that few individuals lived very long regardless of how well they maintained their bodies. Under these conditions, natural selection favors organisms that invest heavily in early reproduction rather than in mechanisms that would keep them alive in a hypothetical safe old age they're unlikely to reach anyway. Aging evolved not because it's beneficial, but as a side effect of prioritizing reproduction over maintenance. This evolutionary perspective helps explain why aging rates vary so much across species. Animals that face high predation risk, like mice, age quickly and die young. Animals that have evolved ways to avoid predators, like birds that can fly to safety or turtles with protective shells, often live much longer. The disposable soma theory also predicts that in protected environments where external mortality risks are reduced, organisms might live longer, which is exactly what we see in zoos, laboratories, and modern human societies with advanced medicine and sanitation. But understanding why aging evolved doesn't tell us how it happens mechanistically. When scientists look at aging organisms, they see damage accumulating at many levels simultaneously. DNA accumulates mutations and breaks. Proteins become damaged and misfolded. Mitochondria, the power plants of cells, grow less efficient at producing energy. Cell membranes lose their integrity. Waste products accumulate inside cells. Stem cells that normally replenish tissues become exhausted or dysfunctional. The immune system becomes less effective at fighting infections, while simultaneously more likely to attack the body's own tissues. One influential theory focuses on telomeres, the protective caps at the ends of chromosomes. Each time a cell divides, its telomeres get slightly shorter. When telomeres become too short, cells stop dividing and enter a state called senescence, or they die. This telomere shortening acts like a cellular clock, limiting how many times a cell can divide. Experiments have shown that artificially lengthening telomeres can extend cells' lifespan in the laboratory, and people with naturally longer telomeres tend to live longer. But telomere shortening can't be the whole story of aging, because organisms like fruit flies and mice have plenty of telomerase enzyme to maintain their telomeres, yet they still age. Another major theory emphasizes oxidative damage from free radicals. As mitochondria produce energy, they also produce reactive oxygen species, highly reactive molecules that can damage DNA, proteins, and lipids. Over decades, this cumulative oxidative damage degrades cellular function. The free radical theory of aging was popular for many years and led to the marketing of antioxidant supplements as anti-aging remedies. But research has shown the picture is more complicated. Antioxidants don't consistently extend lifespan in animal studies, and reactive oxygen species play important signaling roles in cells. They're not just damaging byproducts. More recent research emphasizes that aging involves complex interactions between many different processes. DNA damage triggers cellular responses that can lead to senescence or cell death. Senescent cells that don't die but also don't function normally accumulate in tissues, secreting inflammatory factors that disrupt the tissue environment. Chronic inflammation, sometimes called inflammaging, damages surrounding tissues and impairs the function of stem cells needed for repair. Changes in gene expression patterns alter how cells behave. The microbiome, the community of microorganisms in our bodies, changes in ways that may promote aging. crosslinks form between proteins, making tissues stiffer and less functional. Perhaps the most frustrating aspect of aging research is that no single intervention reliably extends lifespan across different organisms. Calorie restriction, eating substantially fewer calories without malnutrition, is one of the few interventions that extends lifespan in many species, from yeast to mammals. But we don't fully understand why it works, and it's unclear whether dramatic calorie restriction would extend human lifespan or whether modern well-fed humans would tolerate such severe dietary restriction. Some scientists hope that we might develop drugs that target key aging processes and extend healthy human lifespan. Researchers are investigating compounds that can clear senescent cells, drugs that boost cellular repair mechanisms, and ways to rejuvenate stem cell populations. But translating findings from mice or worms to humans is enormously difficult. And aging in humans involves complex interactions between genetics, environment, behavior, and pure chance that make it challenging to study systematically. The deepest mystery about aging might be whether it's truly inevitable. Some scientists believe aging is a disease that can potentially be cured, that there's no fundamental reason why a sufficiently sophisticated technology couldn't maintain the human body indefinitely. Others argue that aging is woven too deeply into the fabric of how complex multicellular organisms work, that the trade-offs between growth, reproduction, and maintenance are fundamental rather than accidental, and that radical life extension may be impossible without fundamentally redesigning human biology. We simply don't know yet which view is correct. The arrow of time. Let's turn now to a mystery that's simultaneously abstract and concrete, philosophical and physical: the arrow of time. Why does time flow in only one direction? Why can we remember the past but not the future? Why do eggs break but never spontaneously reassemble? These questions might seem to have obvious answers. That's just how time works. But when physicists dig deeper, they encounter a profound puzzle. The fundamental laws of physics don't actually distinguish between past and future. They're time-symmetric, working equally well whether time runs forward or backward. Yet our experience of the world is thoroughly time-asymmetric. There's a clear arrow pointing from past to future, from cause to effect, from order to disorder. Where does this arrow come from? The puzzle was articulated most clearly by British physicist Arthur Eddington in 1927. Eddington pointed out that while we have a vivid sense of time's flow, this one-way direction of time makes no appearance in physical science except in the study of organization of a number of individuals. In other words, individual particles and their interactions don't care about time's direction. If you watched a movie of two billiard balls colliding and bouncing apart, you couldn't tell whether the film was running forward or backward. The physics works the same either way. But watch a movie of an egg falling and shattering, and you immediately know if it's running backward because eggs don't spontaneously reassemble. The arrow of time seems to emerge only when we look at systems with many particles, not in the behavior of individual particles themselves. The standard explanation for time's arrow invokes the second law of thermodynamics, which states that entropy, roughly disorder or randomness, tends to increase over time in isolated systems. A shattered egg has higher entropy than an intact egg because there are vastly more ways to arrange the egg's molecules in the shattered state than in the intact state. The second law tells us that physical systems naturally evolve from low entropy states to high entropy states, from order to disorder. This gives time a direction. The future is the direction of increasing entropy. But this explanation immediately raises another question. Why did the universe start with such low entropy in the first place? The Big Bang created a universe that was extraordinarily smooth and uniform. a very low entropy state given the amount of matter and energy present. If entropy always increases, the universe must have started in this special low entropy configuration. But why? The laws of physics don't require it. In fact, from a statistical perspective, a low entropy initial state is extraordinarily improbable. It's as if time's arrow exists because the universe happened to start at a very special point in its possible configuration space, and it's been sliding toward more probable higher entropy states ever since. Some physicists, including Roger Penrose, argue that explaining the universe's initial low entropy requires new physics, perhaps involving quantum gravity or the conditions at the Big Bang. Others propose that our universe might be just one in a vast multiverse where different regions have different initial conditions, and we find ourselves in a region with low initial entropy simply because that's necessary for complex structures like stars, planets, and life to form, a kind of anthropic selection effect. Recent research has explored how the arrow of time emerges at different scales. Some physicists study how quantum entanglement might give rise to time's direction. When particles become entangled, information about individual particles gets encoded in the relationships between them. As systems become more entangled, it becomes harder to reverse their evolution, potentially providing a quantum mechanical foundation for time's arrow. Other researchers examine how the arrow of time works in biological systems, looking at how neurons in the brain respond to information over time and how this might relate to our subjective experience of time's flow. Interestingly, recent work suggests that at the quantum level, time might not have a single fixed direction. Researchers studying open quantum systems have found evidence that quantum mechanics could permit two arrows of time emerging from certain systems, where time reversal symmetry holds in a way that allows time to theoretically flow both forward and backward. This doesn't mean time actually flows backward in any practical sense, but it reveals that our intuitions about time's one-way flow might not apply at the quantum scale. The arrow of time connects to deep questions about causality and free will. Our entire concept of causation assumes that effects follow causes in time, never the reverse. We make decisions in the present that affect the future but not the past. But if the fundamental laws of physics are time-symmetric, is this distinction between past and future as fundamental as we think? Some physicists have even explored the possibility of retrocausality, influences that propagate backward in time, though such ideas remain highly controversial and face serious conceptual challenges. Perhaps most mysteriously, we each have a psychological arrow of time. We remember the past, but not the future. We feel ourselves moving through time from moment to moment, with the present constantly becoming the past and the future constantly becoming the present. This subjective flow of time, what philosopher William James called the stream of consciousness, seems as real as anything in our experience. Yet physics has nothing to say about it. The equations of physics contain time as a variable, but they don't distinguish between past and future, and they certainly don't include anything like our subjective sense of time's passage. Why the physical arrow of time aligns with our psychological arrow remains mysterious. The mystery of memory. While we're considering time and consciousness, let's examine another profound mystery that bridges both. How does the brain create, store, and retrieve memories? Every moment of your life, your brain is somehow recording experiences, encoding them into neural patterns, filing them away for potential later retrieval. Decades later, you can recall events from childhood, remember facts you learned in school, recognize faces you haven't seen in years. This ability to capture and preserve information seems almost magical when you think about it carefully. How does a pattern of neural activity in the present become a stable trace that persists and can be reactivated months or years later? Where exactly are memories stored? How does recall work? How does your brain find the right memory among billions of stored experiences? Neuroscientists have learned a great deal about memory over the past century, but many fundamental questions remain unanswered. We know that memories aren't stored in any single location in the brain. Instead, they appear to be distributed across networks of neurons, with different aspects of a memory potentially stored in different brain regions. The hippocampus, a seahorse-shaped structure deep in the brain's temporal lobe, plays a crucial role in forming new, explicit memories of events and facts that we can consciously recall. Damage to the hippocampus, as famously occurred in patient Henry Molaison after surgery for epilepsy, can prevent the formation of new long-term memories while leaving older memories intact. But the hippocampus isn't the final storage site for memories. Over time, memories appear to be transferred to the neocortex, the wrinkled outer layer of the brain involved in higher cognitive functions. This process, called systems consolidation, seems to happen particularly during sleep. Patterns of neural activity that occurred during the day's experiences are reactivated during sleep, apparently helping to stabilize memories and integrate them with existing knowledge. At the cellular level, memories involve changes in how neurons connect and communicate. When you learn something new, the synapses, the tiny gaps where neurons pass signals to each other, are strengthened or weakened. New synapses may form, while unused ones may disappear. This process, called synaptic plasticity, allows neural circuits to encode information. The neuroscientist Donald Hebb proposed in 1949 that neurons that fire together wire together. When one neuron repeatedly stimulates another, their connection strengthens. This Hebbian learning has become a fundamental principle for understanding how memories form. More recent research has revealed that memory formation is even more dynamic than previously thought. When you recall a memory, you're not simply playing back a recording. Instead, you're reconstructing the experience from distributed neural patterns, and this reconstruction process can actually modify the memory itself. Each time you remember something, the memory becomes temporarily unstable and must be reconsolidated. During this period, memories can be altered, strengthened, or even partially erased. This is why eyewitness testimony can be so unreliable. Each time witnesses recall and recount what they saw, they may inadvertently modify their memories. Despite these insights, major mysteries remain. We still don't know precisely how patterns of synaptic changes encode specific memories. How does the particular pattern of strengthened and weakened connections in a neural network correspond to the memory of your grandmother's face or the feeling of riding a bicycle? We can't yet read out memories from brain activity or predict what someone is remembering based solely on watching their neurons fire. Another puzzle is the nature of memory storage capacity. The human brain has roughly 86 billion neurons, each connecting to thousands of others, creating trillions of synapses. This astronomical number of connections could theoretically store an enormous amount of information. Some estimates suggest the brain's memory capacity might be measured in petabytes, comparable to the entire internet. Yet we forget vast amounts of information. Why are some experiences remembered vividly for decades, while others vanish within seconds? What determines which memories are preserved and which are lost? The emotional significance of memories plays a crucial role in their strength and longevity. The amygdala, an almond-shaped structure involved in processing emotions, enhances memory formation for emotionally arousing events. This is why you likely remember exactly where you were during major life events or shocking news, but you've forgotten what you ate for breakfast 2 weeks ago. The amygdala's influence on memory explains why traumatic experiences can be so difficult to forget and why emotional memories tend to persist longer than neutral ones. Recent research has even revealed that memory might not be exclusive to the brain. In a surprising finding, scientists discovered that cells from other parts of the body can exhibit memory-like properties. When kidney cells and nerve tissue cells were exposed to patterns of chemical signals mimicking the spacing effect in learning, they activated memory genes just as brain cells would. This suggests that the ability to respond to patterns and store information might be a more fundamental property of cells than previously recognized, though the full implications of this finding remain to be explored. Perhaps the deepest mystery about memory is the subjective experience of remembering. When you recall a memory, you don't just access stored information, you have an experience of traveling back in time, of reliving past moments. Philosopher Endel Tulving called this mental time travel, distinguishing between semantic memory, knowing facts, and episodic memory, remembering experiences. When you recall your 10th birthday party, you're not simply retrieving data about the event. You're reconstructing an experience that feels like revisiting that moment, complete with sensory details and emotions. How does the brain create this sense of reliving the past? How do we know we're remembering rather than imagining? These questions connect memory research to the hard problem of consciousness, the great unification problem. From the intimacy of memory and consciousness, let's zoom back out to consider a mystery at the opposite extreme, the fundamental structure of reality itself. Physics in the 20th century achieved two great triumphs: quantum mechanics, which describes the behavior of atoms and subatomic particles, and general relativity, which describes gravity and the large-scale structure of space-time. These theories are each spectacularly successful in their domains. Quantum mechanics underlies all of chemistry and solid-state physics, enabling technologies from transistors to lasers. General relativity has passed every experimental test, from predicting the orbit of Mercury to describing gravitational waves from colliding black holes. But here's the problem. These two pillars of modern physics are fundamentally incompatible with each other. They describe the universe using entirely different mathematical frameworks and contradictory assumptions about the nature of reality. When physicists try to apply both theories to situations where both quantum effects and strong gravity matter, such as the interior of black holes or the first moments after the Big Bang, the equations break down and produce nonsensical infinities. This is one of the deepest problems in theoretical physics. We don't have a quantum theory of gravity. We don't know how to unify our understanding of the very small with our understanding of the very large. The conflict between quantum mechanics and general relativity runs deep. In quantum mechanics, space and time are a fixed background stage on which particles and fields play out their quantum drama. In general relativity, space-time itself is dynamic and curved by the presence of matter and energy. The stage becomes one of the actors. Quantum mechanics is probabilistic and involves discrete quantum jumps between states. General relativity is deterministic and smooth. Quantum mechanics treats time and space differently, with time playing a special role. General relativity treats space and time on equal footing as aspects of a unified spacetime. For nearly a century, physicists have sought a theory of quantum gravity that would reconcile these differences. One of the most developed approaches is string theory, which proposes that the fundamental constituents of reality are not point-like particles but tiny vibrating strings. Different vibration patterns of these strings would correspond to different particles and forces. String theory naturally incorporates gravity and predicts the existence of gravitons, hypothetical particles that carry the gravitational force, just as photons carry the electromagnetic force. String theory is mathematically elegant and has generated profound insights into theoretical physics and mathematics. But it faces serious challenges. It requires the existence of extra spatial dimensions beyond the three we observe. Typically 6 or 7 additional dimensions that must be curled up so small we can't detect them. It predicts an enormous landscape of possible universes, each with different physical laws, making it unclear whether the theory makes any definite predictions about our actual universe. And despite decades of work, string theory hasn't produced any experimental predictions that could be tested with current technology. Some critics argue that string theory has become untestable speculation rather than empirical science. Another approach to quantum gravity is loop quantum gravity, which attempts to quantize space-time itself, treating space and time as composed of discrete fundamental units, like a digital image made of pixels. This approach preserves more of general relativity's spirit, but faces its own mathematical and conceptual challenges. Other physicists explore approaches like causal set theory, which tries to build up space-time from fundamental causal relationships, or theories that attempt to derive space-time itself as an emergent phenomenon rather than a fundamental feature of reality. The quantum gravity problem connects to other deep mysteries. Black holes present a particular puzzle. According to classical general relativity, anything that falls past a black hole's event horizon is lost forever, including information about what fell in. But quantum mechanics insists that information can't be destroyed. This black hole information paradox has troubled physicists for decades. Stephen Hawking argued that black holes slowly evaporate by emitting Hawking radiation, but the radiation appears to carry no information about what fell into the black hole, seemingly violating quantum mechanics. Recent work suggests that information might be preserved after all, perhaps encoded in subtle correlations in the Hawking radiation or in the structure of the event horizon itself. But the issue remains contentious. The quest for quantum gravity also connects to the question of whether the fundamental laws of physics are unique or arbitrary. Is there only one mathematically consistent way that gravity, quantum mechanics, and the other forces can work together? Or are many different versions possible, with our universe simply happening to have one particular set of laws? The answer would profoundly affect our understanding of why the universe has the properties it does, and whether anything like the anthropic principle, the idea that the universe must be compatible with the existence of observers like us, plays a role in physics. The origin and fate of the universe. Let's conclude our journey by confronting the ultimate mysteries. Where did the universe come from, and where is it going? Modern cosmology has made stunning progress in understanding the universe's history. We know the universe is roughly 13.8 billion years old, born in the Big Bang when all space, time, matter, and energy emerged from an initial state of extreme density and temperature. We've traced the universe's evolution from that fiery beginning through the formation of the first atoms, the first stars, the first galaxies, to the vast cosmic structures we see today. But push this story to its beginning, and we encounter mystery. What came before the Big Bang? This question might not even make sense. If time itself began with the Big Bang, then there was no before. But this answer feels unsatisfying. Why did the Big Bang happen? Why is there something rather than nothing? Physics can describe how the universe evolved from a tiny fraction of a second after the Big Bang onward, but the initial moment itself, the singularity where all known physics breaks down, remains impenetrable to current understanding. Some cosmologists propose that our universe might have emerged from a prior state, perhaps the collapse of a previous universe in an endless cycle of expansion and contraction. Others suggest the universe arose from quantum fluctuations in a pre-existing quantum vacuum. Still others argue that our universe is just one of countless universes in a vast multiverse, each with potentially different physical laws, and that universes are constantly branching off from each other through quantum effects or inflating from quantum fluctuations in some higher dimensional space. But all these proposals raise as many questions as they answer. Where did the quantum vacuum or the multiverse itself come from? Can we ever test these ideas empirically, or do they lie forever beyond the reach of observation? The universe's future is equally mysterious and depends crucially on the nature of dark energy. If dark energy remains constant, the universe will expand forever, growing ever colder and emptier. Eventually, all the stars will burn out, black holes will evaporate through Hawking radiation, and the universe will approach a state of maximum entropy where nothing interesting can happen anymore. The heat death of the universe, trillions upon trillions of years from now. If dark energy strengthens over time, the expansion could accelerate so dramatically that galaxies, stars, planets, and eventually atoms themselves are torn apart in a big rip. If dark energy somehow weakens or reverses, gravity might eventually overcome the expansion, leading to a big crunch where the universe collapses back to a singularity, possibly to bounce and expand again in a cyclic model. Which fate awaits us depends on physics we don't yet understand. And even if we could predict the universe's ultimate future, deeper questions would remain. Why this universe rather than some other one? Why these physical laws rather than different ones? Some physicists and philosophers argue these questions fall outside science's scope. Science can describe how the universe works, but not why it exists or why it has the particular properties it does. Others contend that a final theory of physics might explain why the laws must be the way they are, that there might be only one mathematically consistent set of laws that could describe a stable universe, eliminating the mystery of why this particular universe exists. Mysteries as windows to the future. As we've journeyed through these great unsolved mysteries, consciousness, the origin of life, dark matter and dark energy, aging, time's arrow, memory, quantum gravity, and the origin and fate of the universe, a pattern emerges. Each mystery represents not just a gap in our knowledge, but a window into the unknown, hinting at deep truths about reality that we've barely glimpsed. These mysteries humble us, reminding us how much we don't know, despite centuries of scientific progress. Yet these mysteries should also inspire us. Every one of the great scientific advances of the past began with confronting something inexplicable. Newton's laws of motion emerged from puzzling over the seemingly different rules governing heavenly and earthly motion. Darwin's theory of evolution arose from the mystery of life's diversity and the peculiar patterns of similarity between species. Quantum mechanics was forced upon reluctant physicists by the stubborn refusal of atoms to behave as classical physics demanded. General relativity grew from Einstein's meditation on the mysterious equivalence between gravitational and inertial mass. The mysteries we face today may seem impossibly difficult. Some may require entirely new conceptual frameworks, new mathematics, new experimental techniques that don't yet exist. Some may require us to overturn cherished assumptions about the nature of reality, consciousness, or causation. Some may force us to accept that there are hard limits on what science can discover or explain. But history teaches us to be bold in our ambitions while remaining humble about our certainty. We might find that consciousness emerges from information integration in sufficiently complex systems, resolvable through better neuroscience and clearer philosophical thinking. Or we might discover that consciousness requires new physics, perhaps involving quantum effects in the brain or reflecting some fundamental feature of reality we haven't yet recognized. We might create life from scratch in the laboratory, definitively solving the origin of life problem, or we might find that the specific historical pathway from chemistry to biology is lost forever, knowable only in its broad principles but not in its details. We might detect dark matter particles in our experiments, revealing a hidden sector of physics parallel to the one we know. Or we might find that dark matter is something far stranger, primordial black holes or modifications to gravity itself, or some exotic form of matter that interacts so weakly with ordinary matter that we can only ever perceive it gravitationally. We might develop interventions that dramatically slow human aging, or we might discover that aging is so deeply woven into how complex organisms work that it cannot be eliminated without fundamentally redesigning biology. We might find a successful theory of quantum gravity that unifies physics into a single coherent framework, or we might learn that quantum mechanics and general relativity are both approximations to something deeper that we can barely conceive. We might discover that our universe is one of many in a multiverse, or we might find that the universe is a unique, inevitable consequence of logical necessity. The joy of science lies not in having all the answers, but in the process of discovery itself. Each mystery solved opens up new questions, new territories to explore, new phenomena to understand. And even the mysteries that resist solution teach us something valuable about the limits of knowledge, about the nature of explanation, about what it means to understand. As you drift toward sleep tonight, consider the strangeness of your existence. You are a pattern of atoms arranged in such a way that the universe becomes aware of itself. You are made of particles that were forged in the hearts of ancient stars. You carry in your cells the legacy of billions of years of evolution, stretching back to the first primitive organisms in Earth's primordial oceans. Your consciousness, your memories, your sense of self, these emerge somehow from the dance of electrons and neurotransmitters in your brain, though we still don't understand how. You exist in a universe that is mostly dark matter and dark energy, mysterious substances we cannot see or touch. You live in a cosmos that began in a Big Bang 13.8 billion years ago and will continue expanding for trillions of years into a future we can barely imagine. The flow of time that carries you from moment to moment emerges from processes we're only beginning to understand. You age according to mechanisms that involve your genes, your environment, and accumulated damage over decades, growing from infant to adult to elder through processes that remain partially mysterious, even to scientists who study them intensively. These mysteries are not failures of science, but reminders of how much remains to discover. They are invitations to wonder, to question, to imagine. They connect us to the great human project of understanding our place in the cosmos, a project that stretches back to our ancestors staring up at the stars and forward to future generations who will solve mysteries we haven't yet conceived. If you found this exploration of science's greatest mysteries thought-provoking, please consider subscribing to DREAMLAB Knowledge. Hit that like button to help others discover this journey through the unknown territories of human understanding. Share this with anyone fascinated by the deep questions that science has yet to answer, by the intersection of knowledge and mystery, by the quest to understand our universe and our place within it. Your engagement helps us continue producing content that tackles the big questions, that brings together perspectives from physics, biology, neuroscience, and philosophy, that values both what we know and what we've yet to discover. Together, we can build a community that embraces mystery not as an obstacle, but as an opportunity, that sees the unknown not as something to fear, but as an invitation to explore. Thank you for joining this journey into the heart of the great unsolved mysteries of science. And until next time, keep questioning, keep wondering, and keep marveling at the magnificent strangeness of the universe we inhabit.